Welcome to Positive Physics. Today we're looking at infrared radiation. Now, infrared radiation is part of the electromagnetic spectrum, so as with all other sections, has a speed of 3 × 10⁸ meters per second in a vacuum. It can be reflected and refracted. It is a transverse wave and transfers energy from one place to another. Now, the wavelength of the infrared radiation is approximately 10⁻⁵ meters. That's quite small. And in terms of our order of the electromagnetic spectrum, radio waves have the longest wavelength, then microwaves, and we're now at infrared radiation. Every object absorbs and emits infrared. We often think of just hot objects emitting or absorbing infrared radiation, particularly thinking of thermal imaging, but actually all objects do. Now, in the case of my hot coffee that I've got as I'm working here, because it's hotter than its surroundings and there is a temperature gradient, so the temperature here is hotter than the outside, more infrared is being emitted than is being absorbed. So my leaving arrow is much longer than my entering arrow, which means the net result is that thermal energy via infrared radiation is being lost from my coffee. It is cooling down. If I've also got a glass of iced water, now it is cooler than the surroundings. So the surroundings will be emitting more infrared radiation into my iced water than my iced water is emitting out into the surroundings. So we've got a bigger absorption of infrared going on rather than an emission at this point, which means there's a net movement of thermal energy into my water, and my water will increase in temperature. So at some point, if I leave them because I've forgotten about my coffee and my water, they will come to a point when they are at the same temperature as the room. They're in thermal equilibrium with the room. And at this point, the infrared emitted will equal the infrared absorbed, both into my coffee and into my iced water. Now, different surfaces emit infrared radiation and absorb infrared radiation differently. And there are 2 experiments that we can do, which are the required practicals. One is involving a Leslie cube, which is literally just a metal cube with a lid on the top, and we put hot water inside it. We have one surface which is matte black, we have one surface which is shiny silver, and on the other sides we have one surface shiny white and one surface matte silver or metal. Here we have an infrared detector which will measure the amount of infrared being given off by each of the sides. But if we're to conduct this experiment appropriately, we need to ensure that our distance, x, between the infrared detector and the wall of the Leslie cube is always the same. So x will be here, but also you'll have the same distance x when we move the infrared detector to this surface. And what we find is that the infrared emitted by the matte black surface is much higher than the shiny silver, even though the temperature of the water inside the Leslie cube, and therefore the temperature of the metal walls of the Leslie cube, will be identical for both. So we have our matte black surface is the best emitter, and our shiny silver surface is the worst emitter. Now, another experiment that we can perform is with a filament lamp, or an infrared heat lamp, which is giving out a lot of infrared radiation. And we have 2 temperature probes, one painted matte black and one left shiny silver, which are attached to a data logger. And again, the distance between those probes and our infrared lamp must be identical for us to have a fair test. It's one of our control variables. Now here what we see is that the black probe increases in temperature more quickly, but when we turn the lamp off, it loses the thermal energy more quickly as well. Whereas the shiny silver probe doesn't increase in temperature as quickly, but when the lamp is turned off, it loses the thermal energy more slowly as well. if we plot temperature against time. So what we found is that matte black, not only did we find it was the best absorber from our Leslie cube experiment, but we found that it's the, best emitter from our Leslie cube experiment. We found it's the best absorber from this experiment. The infrared is going from the lamp into the temperature probes. Here, the infrared is coming from the surfaces out to the infrared detector. So matte black is the best emitter and also the best absorber. The shiny silver, the worst emitter, it's also the worst absorber of infrared radiation. Now, we often get questions where we have to think about the surface application and therefore which colour we would use and why. And I've put a warning triangle here and said think, because this is where a lot of people lose marks in their exams, because they'll simply write that something should be black because it's a good emitter and absorber of infrared radiation, but they need to be specific for the surface and the application that's being talked about. So let's think about the fridge. If you were to pull out your fridge, and please don't do this, on the back you would find a series of black pipes wiggling backwards and forwards, and they are your radiator. They are designed to remove thermal energy from the coolant, which has passed through the fridge, into the outside surroundings. The idea being we want to cool down the contents of our fridge and get rid of all that extra thermal energy. So they are black, but they are black not because they absorb thermal energy well, but because they are a good emitter. They will get rid of that thermal energy to the surroundings. Some people have hot water solar panels on their roofs. Now don't get confused between solar panels and photovoltaic cells. So a photovoltaic cell is sometimes called a solar panel as well, but that is where we're turning solar energy into electrical energy. A solar panel has a series of black painted pipes which zigzag backwards and forwards across the panel in the roof, and they are being heated by the sun's infrared radiation, and the water in those pipes is being passed through and heated as it goes through, and then that goes into your central heating system and is already preheated a bit, so it reduces the amount of energy needed to heat your house. Now here we also want our pipes to be black, but we want to absorb that infrared radiation from the sun. We want to get that water as hot as possible. Here we were trying to cool it down as much as possible, so it's black because it's a good emitter. Here it's black because it's a good absorber. We want to get it as hot as possible. Now the vacuum flask is often an example that's used when we're thinking about infrared radiation. And what you've got is a vacuum layer which is preventing conduction and convection in order to keep the contents hot or cold. But as we know, we get our infrared radiation from the sun. Radiation can travel through a vacuum. So we have this shiny surface, a shiny silver layer on the outside of our inner bottle in the vacuum flask. But again, we need to think about why it's shiny silver. If I want to keep my coffee hot in there, then I don't want the thermal energy to leave my flask. So I want the surface to be shiny, and I want it to be a poor emitter of infrared radiation. If I've put a nice ice cold drink in there on a hot day, I don't want the thermal energy, the infrared from outside, going into my flask and warming my nice cold drink up. So there I want the surface to be a poor absorber. So that is why we're choosing silver. But you just need to be clear when you're thinking about answering questions. What is the surface application? What's it trying to do? Do we want to absorb or emit more, or do we want to prevent absorption and emission? Now, there's two more things we need to talk about: the Earth's temperature and black bodies. And I think what we'll do is we'll talk about black body radiation first, and then we'll come back to the Earth's temperature. So a black body, a perfect black body, is defined as something that absorbs and emits all the infrared radiation, and the posh word of saying it is that is incident onto it. Now all that means is shining onto it. And if we were to look at two black bodies, one the surface of the sun and two a piece of very hot steel, and if we were to measure the wavelength of the radiation, the electromagnetic radiation of which infrared is a part, coming from those two surfaces, we would find that the intensity, so the amount of each wavelength, would change depending on the temperature of the object that's emitting it. So here we have the sun, the surface of the sun, about 6,000 Kelvin. And we have this big peak, great intensity, huge amounts of power and energy coming from our sun. And you can see that the peak falls within the visible light section of the electromagnetic spectrum. Up here, just longer than the red light, we have infrared, and here, just shorter than the violet light, we have ultraviolet. So that is our range, but our peak is in the visible light section, which is why our sun looks white, bright white, and the light coming from it looks white. But if we're to look at a piece of hot steel, it's cooler, a lot cooler than the surface of the sun, and that peak has dropped. There's a lot less energy being released, and we've peaked in the red area of the visible spectrum. So that is why a piece of hot steel would glow red. The key thing I want you to note from here, though, is the change in wavelength. So it increases in wavelength the cooler your object gets. And that's key for understanding the Earth's temperature. So we've got three things going on. We've got our infrared radiation incident from the sun. Some of it is reflected. It's reflected from the Earth's atmosphere, it's reflected from the clouds, and it's reflected from the Earth's surface. It doesn't have any effect on the temperature of the surface. Some of it is absorbed. So here we have the infrared coming from our sun. It's absorbed by the atmosphere, by the clouds, and by the Earth's surface. Okay? So this will heat up the surface of the Earth. Then we get emission. Now I've used a different colour here to show the wavelength of emission. If you were to compare the temperature of the sun's surface with the temperature of the Earth, I think you would agree that the Earth's surface is quite a lot colder. So that means that the infrared radiation that is being re-emitted from the Earth, from the clouds and from the atmosphere has a much longer wavelength. And this is then emitted from the Earth. So this would be being lost from the Earth's surface. Now, if we didn't have our atmosphere, and if we didn't have the clouds, and we didn't have carbon dioxide, then all the incident infrared that was absorbed by the Earth would be re-emitted, particularly at night when there was no sun to heat the Earth's surface. But because we have clouds and because we have carbon dioxide in our atmosphere, that wavelength which has been re-emitted is absorbed again in our atmosphere and in our clouds and then re-emitted back to Earth. And that's what keeps the Earth's surface warm. That's why you notice a big difference in the surface temperature of the Earth between winter, on a cold night in winter when there's no cloud cover, you'll often find a frost, or a cold night in winter with cloud cover, there might not be a frost, because that cloud has absorbed the infrared radiation which has been re-emitted by the Earth and then re-emitted that back and kept the atmosphere warm. Now, brilliant for keeping us warm at night, but global warming, we're talking about carbon dioxide increasing in our atmosphere. So if the carbon dioxide is absorbing and re-emitting that infrared radiation, keeping us warm at night, if we increase the amount of carbon dioxide that is absorbing the infrared radiation, we'll increase the amount that's being re-emitted. And therefore, our temperature of our surface will rise. We're no longer in our equilibrium situation where what was being absorbed and what was being re-emitted and re-emitted from the atmosphere was keeping the surface temperature constant. I know it's different places on the Earth, but in general constant across the whole Earth. Now we're in a situation where it is gradually increasing because that extra carbon dioxide is absorbing and re-emitting and keeping that infrared radiation in our system here. So there we go. That is infrared radiation.